here we are solving some questions. So here we have a linear transformation that is given to us. So T acts on vectors from R2 and gives us vectors from R3. So the first question is, what's the domain of T? Well, domain is the first, so it's like the input space. The inputs are vectors from R2. So the domain is R2. And the codomain is the space of the outputs. And here outputs are vectors from R3. So that's easy. What's the image of vector 2, -1? Well, that's easy. Just plug it in. 2, -1. So x1 is 2, x2 is -1. So I have 2 minus 1. Then I have 2 times 2. And 2 plus 3 times -1. So this is 3, 4, this is -1. So that's the image of the vector 2, -1 under the action of linear transformation T. The image is 3, 4, -1. What's the standard matrix associated with the linear transformation T? Well, that's easy. To get the columns of the standard matrix, we need to apply T to E1. So E1 is 1, 0. So let's say T of 1, 0. So we have vector 1, 2, 1. Good. And then T of E2, T applied to vector 0, 1. So it's -1, 0, 3. So from here, the standard matrix so I'll write it properly. Basis for the input space, basis for the output space, both of them are standard. So I get the first column is the image of the first basis vector. Second column is the image of the second basis vector. SS. Okay, so that's my standard matrix associated with the transformation T. Now the big question, what's the range of T? Well, T is acting, so we know now that T acts from R2 to R3. So this is a matrix transformation because we have a matrix associated with it. So the action of T is actually represented by the action of multiplication by the matrix over there, this matrix here. So the range of T is equal to the column space of the matrix A with A, this matrix here, 1, 2, 1, -1, 0, 3. Okay, so that's the same thing, we know that. So what's the column space for this matrix? Well, it's the space generated by all linear combinations of the columns. These two columns are linearly independent, so range of T is the same as column of A, which is span of these two columns. So that's very simple. So what's the kernel of T? That's the same as the null space of the matrix A. So the big question, what's the null space of this matrix? Well, I already know that the column space is generated by two vectors, so the dimension of the column space is 2, that means the rank is 2. That means I have two linearly independent columns, so there's no free variables here. When I do the work, you can do the work and find the null space of A, and you'll find that it is only vector 0, 0. So that's straightforward, all of these computations. Another question, we are given a linear transformation that goes from R2 to R2, so this is also called linear operator because the input space and the output space is the same, and the linear transformation is given by these formulas here. So the question is, what's the standard matrix? Well, we know that need to apply the linear transformation to the standard basis vectors for R2. So 1, 0. And then apply to the second basis vector. So the standard matrix is standard matrix associated with the linear transformation T is for standard input, standard output. First column is the image of the first basis vector, and second column is the image of the second basis vector. That's it, finished. So we know already that this is matrix transformation. Yes. And to find the range, our range is just column space of the matrix A, and the matrix A is this matrix, the representation matrix here. We realize that these two columns are linearly dependent. The second one is -3 times the first one. Okay, so we know that the column space is generated by, let's say, the first column. Right? Because these two columns are linearly dependent. Okay, so now I need to find the kernel of the linear transformation, and we know it's equal to the null space of the matrix. So what's the null space? Well, I need to solve AX equals 0. Well, 0 here is 2 by 1. So I need to solve this system here. So I already know that I have only one linearly independent row. Why? Because I have only one linearly independent column. And if you check, second row is -2 times the first row. So all I need is one of the equations. So I have x1 minus 3x2 equals 0, which means x1 is 3x2. So the solution, x1, x2, is 3x2, x2. So I treat x2 as a free variable. And now I factor it. So I get this. So the null space is span of this vector here. So that's what we have. Kernel of T is the same as the null space of A, which is span of the vector 3, 1. So those things are pretty straightforward. There's nothing special here. Another problem, we are given another linear operator from R3 to R3. So this is the definition. We need to find the standard matrix for this linear transformation. It's obviously also a matrix transformation, so I don't need to repeat that for nothing. So how do we do it? Well, as usual, apply the linear transformation to the basis vectors of the standard basis, and then put those results into a matrix. So what do I have here? 0, 1, this is x1, I guess, 3, second basis vector, apply the linear transformation to the second basis vector, -2, 0, and apply the linear transformation to the third basis vector, or the standard basis. Okay, so the standard matrix is with standard input, standard output. First column is the image of the first basis vector, second column is the image of the second basis vector, and the third column is the image of the third basis vector. So that's the standard matrix. So what's the image of this vector? So what is T of 2, 1, -3? Well, we have two ways. Either I plug it in, so that's one way, the other one I just multiplied by the standard matrix. So I'll do both just to see what happens. So it's -3 here, and then 2 minus 2 is 0, and then we have 6 minus 3 is 3. So this is the image of this vector under the transformation, or another version. -3 is equal to the product of the representation matrix, the standard matrix here, with the coordinates of the vector 2, 1, -3 in the standard basis, which is the same as the vector, we know that. Coordinates of a vector in the standard basis are equal to the components of the vector. So if we do the product, so we have -3, okay. Then we have 2 minus 2 plus 0, that's 0. Then we have 6 minus 3 is 3. So these are the coordinates in the standard basis, which are the same thing as the vector itself. So we got the same result, obviously. The image of the vector under the linear transformation can be obtained by plugging directly, or by multiplying the coordinates of the vector in the standard basis by the standard matrix, and then converting the result. But we know that the vector and its coordinates in standard basis are the same. Now, question, how about range? So what's the range? So since this is a matrix transformation and this is the representation matrix, so So range is equal to the column space, right, of the matrix. So I'll write column space of the representation matrix. Well, if I check this matrix and I compute the determinant, for instance, I'll get the determinant is 6, just for fun. The determinant is negative 2, 0, negative 2, okay, so that's 6. Okay, so this means this matrix is invertible, which means all 3 columns are linearly independent and all 3 rows are linearly independent. Okay, so that means that the column space is actually R3. Why? Well, if all 3 columns are linearly independent, then they are basis for R3, obviously, because these are 3 linearly independent vectors in R3. So the range is R3. Ah, that's interesting. What's the kernel of the transformation? Well, that's a null space, as we know, of the representation matrix. So what's the kernel here? All people that are sent to 0. Well, this is invertible matrix. So the solution of Ax equals 0 is unique, and that's vector 0. So the null space is only the vector 0. So that's cute. So that's how our knowledge from before is useful here. Here we have another example. We have this time 2 linear transformations. One is the operator from R3 to R3, given by this expression here. And the other linear transformation goes from R3 to R2, and this is the formula for it. So first thing, let's try to find the standard matrices for each one. So the standard matrix for T1, so what we need to do is apply, remember, it's T of E1, and T of E2, and T E3, right? So what's that? So first basis vector from R3, 1, 0, 0. So we put 1, 0, 0 here. So x1 is 1, x2 is 0, x3 is 0. So we have 3, negative 1, 0. Second column is the image of the second basis vector, so 0, 1, 0. So x2 is 1 and the other guy is at 0. And the third column is the image of the third basis vector, 0, 0, 1. So this is 5. So that's the standard matrix for T1. Okay. We can also compute the determinant for this one. So it is going to be 6, negative 6. So this matrix is invertible, so that means that this transformation is also invertible. That's just an observation, nothing else. So we have a standard matrix for this guy. So knowing that this matrix is invertible, what's the range of T1? Well, the range of T1 is column space of the matrix. So I'll just write it here. So what's the column space? Since all 3 columns are linearly independent because the determinant is different from 0, that means it's R3. And the kernel of the linear transformation is the null space of the matrix So since this is invertible, x equals 0 has only one solution, which is vector 0. That's just cute. We don't need to do this all the time, but it was just fun. So how to find the standard matrix for T2? Well, the same process. First column is the image of the first basis vector. Second column is the image of the second basis vector of R3. And the third column is the image of the third basis vector of R3. I keep writing these because they will be very useful later on. So this means standard input, standard output, standard basis for input space, standard basis for output space. Okay, so first basis vector 1, 0, 0. So we have -1 and then 0. Second basis vector 0, 1, 0. 1, -1. And the third basis vector is 0, 0, 1. So the first component will be 0, and this is 1. Obviously, this matrix is not square, so it's not invertible at all. We cannot even talk about invertibility here, because it's not square. So the range, what would be the range? That's column space of the matrix here. T2 SS. Obviously the two rows are linear independent, so only two columns are independent. So its span, let's say first column and second column, because they are independent. What is this? So span of these two guys, these are two vectors from R2 that are linearly independent, obviously. So they are basis for R2. So span of this is actually R2. Wow. But this linear transformation sends people to entire R2. Okay, so the range is actually R2. So what is the kernel? That's the null space of this matrix here. So what's that? Oh, we need to solve this thing x equals 0. So what do we get? Quickly, x1 is equal to x2 and x2 is equal to x3. So that means span of, so everybody is equal to everybody, 1, 1, 1. Nice. So that's the kernel. So this span of this vector is the null space of the matrix, which is the kernel of the transformation. That means that any scalar multiple of this vector is sent to 0. Okay, so that's cute. Now we could compute the composition. So let's compute. So find the standard matrix of the composition. Now we need to be careful, we cannot just compose anything with anything. This guy goes from R3 to R3, and the other guy goes from R3 to R2. So we can go T1 and T2. Okay? Because we first act with T1, we take people from R3 and we bring them to R3 with T1, and then we take them from to R3 and then from R3 to R2 with T2. Okay, so this thing goes from R3 to R2. So we already know that the standard matrix for this composition is simply the product of the standard matrices in the correct order, obviously. So let me copy the matrices here. Okay, so now all we need to do is just multiply. So -3, -4, and 0, 0, 0, then 0, 2, 0, okay, then 0, 1, 0, 0, 0, 1, and then 0, -2, and 5, that's 3. So this is the transformation, the standard matrix associated to the composed transformation. Okay. So obviously, again, we could find the kernel and the null space. That's not a problem. And also range, that is the column space of this matrix, which will be R2. So no need to do that unless it is asked. So we have this composed linear transformation, and its standard matrix is this one. So if we want to know how this matrix acts actually, so we can write it in a compact way. So if I apply this to a vector x1, x2, x3, actually it's this matrix times the coordinates of the vector. You don't need to do it if it's not asked, but it's always fun. So we have -4x1 plus 2x3, and then x1 plus x2 plus 3x3, which is the same as, because these are the coordinates in the standard basis, but the coordinates in the standard basis are the same as the vector itself. Okay, so that's what it means, the composed linear transformation. Obviously, the composition in this sense not defined, because T2, we check, takes people from R3 to R2, and T1 takes people from R3 to R3. So once you got here, there's no way to do anything, because T1 cannot act on vectors with 2 components, it acts on vectors with 3 components. So you see, you cannot swap the order. Order is super important. So these are very straightforward concepts. They're not complicated in itself. A little bit of practice will help, just to be comfortable in building the standard matrix, and from time to time finding the kernel and the null space of the, so kernel of T is the null space of the representation matrix, and range of T is the column space of the representation matrix. So you can practice that also.